Interest in this webinar and to our panelists for being with us today. My name is Alan Rowsome. I'm Executive Director of the Northern Virginia Conservation Trust, and I'd like to welcome everyone to NVCT's third installment of our Changemakers webinar series, Today's Weather, Tomorrow's Climate. NVCT is your regional land trust for Northern Virginia, and we've worked across our area for the last 27 years to protect nearly 8,500 acres of forests, streams, trails, and wildlife habitat for future generations to enjoy. We know that as a land trust, we have an opportunity and in fact an imperative to meet the challenges of climate change, and that protecting natural areas as open space is one of the most effective things we can do to mitigate for the changes we're seeing. 3 years ago now at our spring conservation luncheon, we welcomed Jason Samenow to the stage to give a presentation on how weather patterns are affecting our region. And it seems fitting on another blazing hot summer day that we have him back here today to see how things have evolved. Northern Virginia and the entire world for that matter are seeing some of the most severe and unprecedented weather on record, and understanding how we deal with what's coming while continuing to save nearby nature is at the core of what we at NVCT do. It's now my pleasure to introduce you to NVCT board member John Hopewell. John grew up in Falls Church, but headed out west for college, getting a degree in earth science from Montana State University. After graduation, he worked on a backcountry trail crew in Yellowstone National Park with the Montana Conservation Corps. He's also worked at the Mount Washington Observatory in New Hampshire and for the National Center for Atmospheric Research. He has a master's in environment and development from the University of Amsterdam and currently teaches earth science at Justice High School in Fairfax County. He's a regular contributor to the Capital Weather Gang, and we've been lucky to have him on the NVCT Board of Directors for the last 6 years, where he has served as treasurer and vice chairman. John, welcome, and thanks for doing this.
Thank you. I've been looking forward to it. You can hear me? Am I broadcasting?
Yep, you're good.
All right, great. So welcome everybody. Thanks for joining. So maybe you're sitting there thinking to yourself, what does a land conservation outfit have to do with climate change? Well, a lot. When we talk about climate change, we talk about adaptation and mitigation. How do we adapt and how do we mitigate the rising temperatures and the increasing precipitation, flooding, et cetera? Mitigation. The mitigation business is what NVCT is in. And we go out there and we preserve canopy cover, we preserve pervious surfaces, and we're not anti-development, but we think there's a good mix between preserving green space and development. Higher temperatures and more floods, Jason's going to talk about. And it's quantify what's actually happening with our changing climate. Also, NVCT is kind of a unique land trust in the United States because we service a urban area. Many land trusts are in rural areas, but here we have urban setting and what's known as the urban heat island effect. This is where concrete and dark surfaces, everything associated with the cities absorb solar radiation in the daytime, increasing the temperatures, but also at night, it slowly emits that radiation back in, warming the night as well. But with canopy cover, temperatures can be reduced dramatically. And our parcels in Arlington and Fairfax and Loudoun, all these areas, by doing this, we're increasing quality of life, really, and mitigating climate change. So actually, Mary, can you show the thermometer pictures? I did an experiment. I'm a high school teacher, okay? I do this with my students. And I took a thermometer outside and I put it in the grass, under the shade, and then I put it in my driveway, 20 feet away. And this is 30 minutes ago. The ambient air temperature was 86. So if you're standing in the sun, it would have been 86. If you're in the grass, in the shade, it's 80. And I think that I can't see it because I'm blocked, but I think it was 103 in the driveway. So this is what we're talking about when we preserve canopy cover and we preserve open spaces that are not paved. So our mission is to save canopy cover, pervious surfaces, mitigate the impacts of climate change, increase quality of life in Northern Virginia. And it's in line with many policymakers, local jurisdictions, policymakers, and comprehensive plans. So enough from me. Without further ado, let me introduce my good friend and colleague, Jason Samenow. I've known Jason since we were kids at Sleepy Hollow Elementary School. And I remember during snowstorms, I'd be outside throwing snowballs, but Jason would be with a thermometer taking measurements and collecting data. And now I work for him on the side, so it's great. He's built an amazing multimedia weather communication giant with some of the most talented writers, meteorologists in the country, and I'm proud to be one of them. Jason's a local boy. He went to UVA, got a bachelor's in environmental science, then he went off to the powerhouse University of Wisconsin-Madison School of Atmospheric Science, got his master's degree, worked at the EPA Climate Division for several years and where he started Capital Weather Gang, which was a blog, but it got so big that the Washington Post brought him on. And it's the local go-to source of weather information and national stories as well, international. So, Jason, take it away.
All right, thanks so much, John. I really appreciate that introduction, and great to be on a panel with you as far back as we go. And of course, your contributions to the Capital Weather Gang, your ski reports, your articles on nature and the environment are terrific, and I know our readers really enjoy and appreciate those. So, and also, Alan, thank you for having me here today. So, of course, we hear about climate change all the time, and we hear about how it's affecting faraway places, and we hear about how it is expected to impact human health and the environment decades into the future. But what we don't hear about as often is, what is climate change doing in our own backyard? How is it influencing weather, and what are the changes we're seeing right now? So that's what the core of my presentations focuses on, is the changes we've already seen here in the Washington region, which are actually pretty dramatic in a lot of respects. And we'll also look ahead as to what the future may look like as the planet continues to warm, and by extension, our region. So let me go ahead and share my screen, and we can hop right into the presentation here. So I will advance the slides. And first of all, just give you a little bit of background about the Capital Weather Gang. John said some very nice things, but I'll give you a little bit of an overview, or CWG 101, so to speak. We are the Washington Post weather team, and we provide forecasts for the DC area in the morning and the afternoon. We update the forecast. And of course, when there are major weather events, we're covering those live, and pretty much 24/7 when there are significant snowstorms, hurricanes, severe thunderstorms, and whatnot impacting the region. But our content expands well beyond the DC area. We also cover major national and international weather stories. And we also write about important scientific developments in weather science. We do many articles on climate change and how it's impacting the weather and the environment, both locally and nationally and internationally. Of course, this summer we've had, with all of the punishing heat waves we've seen in the West and the drought, we've been covering that in a lot of detail and a lot of depth, as well as the connections to climate change there. Our content, it spans across platforms. So the hub of what we provide is offered at washingtonpost.com/Capital Weather Gang. But we have very active social media presence on Twitter at Capital Weather, and on Facebook, facebook.com/Capital Weather. Some of our stories that we post online are then put into the Washington Post print edition. And I should mention that we have a radio partnership with WAMU 88.5, the local NPR affiliate. We do forecasts for the morning and afternoon drive on Monday through Friday, and Saturday as well. Actually, now we do Saturday morning forecast updates. For our local weather coverage, we put a real emphasis on reader engagement, because weather is something we all share together. And so we try to make it a two-way conversation. It's not just us providing weather information to our audience, it's our audience also feeding back and sending us in storm reports, sending us photos, multimedia. And so basically providing ground truth for the forecast we're providing. And so if a storm's moving through the region from west to east, we get photos of the storm and reports of the impacts which are happening in Leesburg, and as they roll through Fairfax and then Arlington and then the district and then into our eastern suburbs all the way out to Annapolis. We are getting those reports from our readers and incorporating those into our coverage, also answering their questions and trying to keep them as informed and as engaged as we can. We also put a real emphasis on communicating uncertainty, understanding that weather is, of course, an imperfect science, and for snowstorms and high impact weather events, there often are a range of possibilities. And so we like to illustrate what those possibilities are, what the high end ranges, the low end ranges are, and what the chances are our forecast, our most likely forecast will be right or wrong. And then we also like to express confidence in our forecast because we have higher confidence in some forecasts and lower in others. So that's just sort of a snapshot of what we do. As John mentioned, we have a large team of contributors. There are two of us who are full-time, myself and my deputy editor who just started last week, Kasha Patel. And we're also in the process of hiring a staff meteorologist right now. So you know, anyone who wants to work for our group, you can message me and I can send you the link for applications. Anyways, again, our coverage, the bulk of what we do, you can find at washingtonpost.com/capitalweathergang. So let's talk about climate and weather and what's happening and how it's affecting the region here in DC. To start off, you know, thinking globally and thinking about how our atmosphere is changing and evolving. We have measurements of carbon dioxide in the atmosphere dating back hundreds and even thousands of years. And but what we've seen, if you look at the curve I'm showing you here, is the carbon dioxide concentration basically from 1750 to 2020, as of just a couple of days ago. In fact, the latest measurements from Mauna Loa on the Big Island of Hawaii, where they take these measurements. And so this chart here is showing the concentration of CO2 in the atmosphere in parts per million. And so during the Industrial Revolution, or before the Industrial Revolution in the late 1700s, the CO2 concentration in the atmosphere was 280 parts per million. That has since risen to 420 parts per million, basically as of a few days ago. So we've seen about a 50% increase in atmospheric carbon dioxide in the last couple hundred years, and a steep increase since the 1950s. We're adding about 2 to 3 parts per million of CO2 into the atmosphere every single year. And so we'll probably double the concentration, the pre-industrial concentration of CO2 in a matter of decades. So the CO2 is, of course, a heat trapping gas. All other things being equal, you add carbon dioxide into the atmosphere, it will make the climate warmer. And we see that on the next slide here, which shows a time series of temperatures dating back to the late 1800s and extending to 2020. This is a global average temperature difference from normal year by year, and based on an average temperature in the 20th century, so from 1901 to 2000. And so years which were colder than that 20th century average are illustrated by blue bars in this chart. And the years, so you can see basically from the late 1800s to the early 1900s, most years were cooler than the 20th century average. But then once you get to basically 1976, the year John and I were born, every year has been warmer than the 20th century average. So that was we kind of hit an inflection point in the mid-1970s when the climate has been warming steadily. And the last 7 years have been the warmest on record. 2020 was the second warmest on record, and 2016, I believe, was the hottest year on record. But all 7 of the warmest years have been since 2014, and we've had 44 straight years warmer than that 20th century average, as you can see by all these red bars from 1976 to present. It's not just warming globally. That was a time series of global average temperatures. This shows you how temperatures have changed in the United States since the beginning of the 20th century, or the rate of temperature change, I should say. And you can see red all over the US, indicating almost the entirety of the US has been warming. Some of the most pronounced warming is focused in the Northeast, the Southwest, the Northern Central US, as well as Alaska. In fact, Alaska is warming more than any other area in the US, and that stands to reason, as the high latitudes in the Arctic are in fact warming about 2 to 3 times as fast as the lower latitudes, but pretty much everywhere across the entire world is warming, and that holds true in the lower 48 states as well. 8 of our 10 top warmest years have been since 1998. 2012 and 2016 were the 2 warmest, and we've had 23 straight years of above normal temperatures in the US. So talked about CO2 and how it's influencing temperatures globally and into the lower 48 states. But on a very local level, we have something else going on, which John mentioned in his opening comments, which is the urban heat island effect. And so in urbanized areas, and areas where you have concrete, asphalt, dark surfaces, you have more heat being absorbed by those surfaces, which makes urban areas substantially warmer than surrounding locations. So in addition to the impacts of increasing the carbon dioxide concentrations in the atmosphere, which affects everyone, in cities we have a sort of an intensified warming happening because of urbanization and changes to the built environment. And sometimes you can see changes, really big changes between downtown areas and surrounding rural areas, where if you look at like Dulles Airport and National Airport, on a clear, calm morning, National Airport, which is firmly in the urban core, can be 10 degrees warmer than Dulles. So, you know, like maybe like if you look at Saturday morning, we're going to have clear skies, high pressure over the area Friday night. That should allow a relatively refreshing night for the DC area in late July. But by Saturday morning, the low at National Airport might just be 65, whereas if you go out to Dulles, it might be 55, just because less development out there and more of the heat, which collects during the daytime, can escape at night rather than being retained by all of the asphalt and concrete and dark surfaces that are in the urban zone. So let's just show you a little bit about the development in the region and how that plays into our climate. So this map here is a illustration of the percentage of impervious surface area in 1984. And the darker areas show you where you have more impervious surface area, where there's more concrete, asphalt. And impervious surface area, in other words, are materials that that water just runs off of, that it doesn't soak into the ground, and they tend to be heat absorbing surfaces, and they're indicative of where you have more infrastructure, more built environment. So you can see that obviously the downtown Washington urban core there, and you know, some development around Springfield, Tysons, and up towards College Park and elsewhere. So this is 1984, but we're going to fast forward now to 2010, and you're going to see how the percentage of impervious surface area increases dramatically. So here's 1984, let's step ahead to 2010, and you can see how much more blue there is by 2010. I mean, just a lot more development inside the Beltway and outside the Beltway. We'll step back again so you can see it again. 1984, 2010, just a lot more blue and dark blue, showing that increased development in our region. And I'm hoping to get the 2020 look at this soon, so I can add this to the presentation. It will be even more pronounced. So that just shows you there's just more, there's less green space, and more buildings, more paved over area, and that has an influence on temperature. And we can see that here actually. If we look at temperatures in the district on a very hot day, this was there was actually a group of researchers from Portland State University who went around the district on August 28th, 2018, taking temperatures all around the city, and in both the developed areas and in the park areas, to get a sense as to how temperatures differ even in a very localized area over the course of miles on a hot day. And what's interesting is if you look at downtown DC and places in Northeast Washington, temperatures were in the 90s to near 100 degrees, but in Rock Creek Park, in the upper left part of the screen, the temperatures were in the mid 80s. So you could see, in other words, just within a course of miles, maybe it would, you could basically walk 15 or 20 minutes between Rock Creek Park and Northeast DC and see a change in temperature of about 17 degrees, which just shows you how much the built environment matters and how much green space matters in terms of local temperature. And what's interesting is if you look at, you know, where all these oranges and reds are and where the blues are, corresponds, you know, almost exactly as to where the impervious surface areas and impervious surface areas are in the area. If you look at Rock Creek Park in this image of 2010, you see it's all white. Then you see the downtown urban core in blue. Well, that's exactly where you have the higher temperatures downtown and then the lower temperatures in Rock Creek Park. So anyways, as a result of both global and local scale climate change, we're seeing a shift in our temperature distribution. Basically, we're seeing more hot weather, more extremely hot weather, and less cold weather and extremely cold weather. It doesn't mean we don't have cold weather anymore. I mean, we still have cold winter days. We can still have, you know, an unseasonably cool day in the spring or the fall, you know, given the weather pattern. But what climate change is doing, both the local scale effects from the urban heat island effect and the greenhouse gas effects, is it's increasing the likelihood it's going to be hot and extremely hot. I mean, now we're going to set records, and we're going to see fewer record cold events. If we look at DC's temperature history here, from the late 1800s to today, our average annual temperature in the late 1800s was about 54 degrees. Now we're up to about 58, 59. So we've seen about 5 degrees of warming in Washington since the late 1800s, averaged over the year, which is a lot, actually. And again, that is due to both urbanization and climate change. We can also see this if we break it down month by month. And one way we evaluate temperatures in our areas by considering 30-year averages, or what we call normals. And what we consider climate normal shifts every 30 years. So currently our normal temperatures are based on average temperatures from 1991 to 2020. But prior to this year, our averages were based on the period 1981 to 2010. And we can see in this chart that the averages from 1981 to 2010 increased once we shifted forward to looking at averages from 1991 to 2020. And we also have in this chart the 1971 to 2000 averages, and they're in different shades of brown. So the lighter shades of brown indicating the average temperatures from 71 to 2000, and then the darker shade of brown from 1991 to 2020. And you can just see sort of how every month of the year we've seen our average monthly temperature going up. So now in July, our average monthly temperature is 81. It used to be in the upper 70s in the earliest averaging period from 71 to 2000. So you can just see, this is just an illustration of how we're warming across the board as we look at averaging periods. Our hot days are increasing. We're always keeping track of how many 90-degree days we have each summer. And in the late 1800s, we averaged about 25 or so 90-degree days per summer. Now we average about 40, so a steep increase in the number of 90-degree days per summer on average. This summer we're already up to 28, I think maybe 29 as of today. So we're well on pace this year to hit our average of 40, even though it hasn't been that hot of a summer, to be honest. I mean, we're running near average or a little bit above average in terms of the 1991 to 2020 normal, but even so, we've had a large number of 90-degree days. So even in what seems like a tolerable summer now, that would have been an extremely hot summer 140 years ago. Some of our 3 hottest summers on record were from 2010 to 2012. We're also seeing a dramatic increase in our extremely warm nights. That is, nights that don't drop below 80 degrees. It was almost unheard of to have a night that didn't drop below 80 degrees prior to 1999. That it only happened 26 times. But since 2000, it's happened 39 times and 34 times in the last decade. And so more than half of our nights, which haven't dropped below 80 degrees, have occurred since 2010. We haven't had any this summer, actually. Again, this summer, even though we've had a good number of 90-degree days, we haven't had exceptional heat. Our hottest temperature so far is 97, and our nights haven't been too bad. And that's due to the overarching weather pattern, which has actually kept a lot of the extreme heat in the Western United States, where of course they've had a lot of records, and they're in the midst of a terrible drought. Anyways, this next slide, I'm not going to read the whole thing to you because it's incredibly wordy, but it's basically a laundry list of all the heat milestones we've had in the DC area since 2010 that I'm keeping track of. I'll read off a few of them, but we've had our warmest 3 years on record, our 2 top warmest springs, our hottest 5 summers. That's illustrated in the graph on the right side of the slide. We've had our warmest fall, our 3rd warmest winter, our warmest February, March, April, May, and it goes on and on. We've also set all sorts of milestones for our most 90-degree days in a year since 2010, most 95-degree days in a year, and so forth. So there are just many, many indicators that our climate is rapidly warming up here, and pretty much all of our large majority of our heat milestones have been set in the last decade. If you don't believe thermometers, you can look at indicators based on nature, and one indicator of our warming climate is cherry blossoms are blooming earlier and earlier in the spring. Back in the 1920s, when we first started to track when the cherry blossoms hit peak bloom, the average peak bloom date was around April 4th or so. Now the average peak bloom is around March 30th, March 31st. So basically things have shifted forward about 5 degrees as spring temperatures have gotten warmer sooner, and winter temperatures have basically eased, or the extreme cold of winter has been easing earlier and earlier. And so the cherry blossom blooms, just one indicator of that. I mean, obviously there's a lot of noise. Year-to-year weather affects exactly when the bloom occurs, but what you want to look at is the long-term trend, which is towards earlier peak blooms. All right, so clearly temperatures are on the rise, unambiguously, and we're seeing more extremes in terms of, especially in terms of heat. And we're seeing less extreme cold. I didn't talk about that as much, but we rarely see record cold in the winter anymore. The last 2 winters, our coldest temperature is 23 degrees, which was the warmest winter low temperature on record, set 2 years in a row. We're just not getting that cold. Now, it's not to say, given the right pattern, we might not see some extreme cold in the winter again. Weather factors can still align in the face of climate change for cold, but we're just seeing less and less of it. So let's look at rain and snow. And so basically, you warm up the atmosphere, you speed up evaporation, you put more water in the atmosphere available for storms and downpours. And we see that through a number of indicators. First of all, it's getting more humid. We actually did an analysis at Capital Weather Gang looking at how humidity has changed since 1970 at several locations in the region. And we see a general 5 to 10% increase in humidity since 1970. And that makes sense because, again, if you heat up the atmosphere, you're speeding up evaporation, you're putting more water from the land surface into the air. So it's going to be stickier, muggier, steamier. And that's what this time series here is showing at several different locations. And we've also seen that playing out in terms of some precipitation extremes here in the region. 2018 was Washington's wettest year on record. We had 66 inches of rain that year, or rain and or melted snow. And our average annual precipitation is about 40 inches. So that was more than 50% above our average. During that year, we had 24 days with at least an inch of rain. So that's almost a month, which is a lot of days with almost an inch of rain. And we've also had some hydrological or wet weather extremes in the last couple of years as well. Some of you may remember in July of 2019, we had an exceptional downpour on July 7th in both the district and Arlington, which caused a lot of flooding, severe flooding in some areas. 3.3 inches came down in 1 hour at Reagan National Airport. So there were a lot of scenes of just really rapid water rises in our area waterways, which flooded roads, and you had cars stranded in high water, and high water rescues during the morning commute on that July 7th day. Last year, we had our 7th wettest year on record. We had a record 7 days with at least 2 inches of rain. So just in the last 3 years, we've set records for our most days with 1 inch of rain in a year and our most days with 2 inches of rain in a year. And not to mention, we had the exceptional floods in Ellicott City in 2016 and 2018, which were both considered 1 in 1,000 year events. Just exceptional rains, like 6 inches of rain, 6 to 10 inches of rain falling in just an hour or two, which is remarkable. So basically, with faster evaporation, there's just more water in the air for downpours. Now, at the same time, our average snowfall is declining, and that reflects the fact that our climate's warming. So basically, what's happening is, especially early in the winter and late in the winter, precipitation, rather than falling as snow, is more frequently falling as rain. So we're just seeing, or if it snows, it's not accumulating. It's not cold enough for the snow to stick. And so snowfall measurements, you can only measure snow if it's sticking. If it's melting when it hits the ground, it doesn't count. And if we look at 30-year averages of snowfall beginning in the late 1800s to today, we can see that in the late 1800s and early 1900s, we averaged between about 20 and 23 inches of snow a year. Now we average under 15 inches a year, which is pretty sad for snow lovers like myself. But yeah, I think we're down to 14.1 inches for our average snowfall based on the 1991 2020 averaging period. And again, we're losing that snow sort of in the shoulder seasons in November, December, and in March. So it's just not, it's either rain rather than snow, or the snow isn't sticking. And we kind of see that in terms of the our change in the number of accumulating snow events per year since the late 1800s. And during those days, we would average about a half dozen 1 inch or greater snow events per winter. Now we're down to an average of about 3 or 4. So just less opportunities now due to the fact our climate's warming and snow's not sticking or it's falling as rain. But good news is, if you like snow, we're not seeing a change in the big ones. In fact, we've seen a disproportionate number of really big snowstorms, not only in DC, but also throughout the Northeast since 1990. Here in DC, we've had 5 of our 10 top biggest snowstorms since 1990. Same holds true in Baltimore and Philly. New York's had 7 to 10 of their biggest since 1990, and 6 to 10 of their biggest in Boston. So we're still getting the big ones, and usually for the big ones, there's enough cold air in place so that it's not a question of rain or snow, it's just a question of how much. And if climate change is putting more moisture into the atmosphere, our snowstorms may be able to draw more from that. So the big ones could still get bigger, even though we're seeing a decline in snowfall overall. So it's kind of this idea of less snow, more blizzards in a climate change scenario. So we'll see if that holds. There's some research trying to figure out exactly what's going on here. But anyways, that's a trend we see, is that we're not seeing a change in the big ones, maybe even an increase in those because of more moisture available in the atmosphere. I should talk about coastal flooding and sea level rise, because that is an impact in the area, especially for people who live along the Potomac River and along the Chesapeake Bay. We are seeing the sea levels rise due to the fact the climate is warming up. And as the climate warms up, the oceans expand, glaciers melt, which add more water to the ocean, and the ice sheets over Greenland and Antarctica melt and also add more water to the oceans. And here in DC, we've seen about a 1 foot increase in sea level rise over the last 100 years. And that plays into the amount of coastal flooding we see, when we have astronomically high tides, when we have storms moving up from the south, pushing south winds up the Potomac River and up the Chesapeake Bay. There have been studies done by NOAA, which has looked at the incidence of high tide flooding at numerous locations across the mid-Atlantic. And that's shown in the chart on the right, where you see all of the blue bars and the orange and red bars. So in the 1950s and 1960s, where we have tide gauge measurements, it would flood on an average between 0 and 2 days a year in some of these mid-Atlantic locations. But what you'll notice is if you sort of move your eyes toward the right, towards 2000, 2010, 2020, you see a lot more oranges and red, indicating that we're seeing high tide flooding between 6 and 10 times per year. So there was a report done by NOAA in 2014, which found a 300% increase in the incidence of what they call nuisance flooding in the district in the last 90 years. And nuisance flooding basically refers to sunny day flooding, or flooding when you have when you don't have a big storm, but you just have due to the alignment of the moon and the phase of the moon, unusually high tides. And because the sea levels are rising, when we have these spring tides or astronomically high tides, we're seeing waters, inundate low-lying areas like Old Town, Georgetown, Annapolis, and places like that. So, and we'll see that trend continue into the future as sea levels rise. So let's talk about the future a little bit. This is kind of an interesting picture of water flooding the tidal basin into the National Mall during a big event, during a big flood event in 2018. And this is the type of thing we may see more of in the future. But let's first start off talking about heat. And right now, based on the current climate, which is shown on the left-hand side, we average about 8 to 10 days each summer where it gets to 95 degrees or more. Now, as we head into the future, this is a climate model projection that was done for the District of Columbia in 2015. Depending on the emission scenario, how much CO2 we're adding into the atmosphere, we expect pretty dramatic increases in the number of 95-degree days we see each summer. So by 2075 to 2094, if you look all the way to the right, for the low emission scenario, the light orange, we're expected to see about 30 to 35 95-degree days for summer, and around 70 for the high emission scenario during that time period. So basically, the majority, 2 months of the summer, we'd have highs hitting 95, which would be pretty punishing, considering that right now we only average 8 to 10, and that'd be pretty dramatic. So this just goes to show that if we're able to stay on a lower emissions path, and our future looks more like the light orange than the dark orange, we'll have fewer of those 95-degree days, but a certain amount of climate change is locked in. And so invariably, we're going to see more of this hot weather as we get into the later decades of this century. We'll also see increases in heavier rainfall. Not as much. It's not expected to increase as quickly as the heat does, but right now we average about 10 days per year with an inch or more of rain. By 2075 to 2094, we're looking at 13 to 14 days with at least 1 inch of rain, depending on the emission scenario. But rainfall doesn't respond quite as quickly to the increase in greenhouse gases in the atmosphere as temperature does. But still, the trend will be towards wetter conditions if these climate projections are correct. And 2018 was a sneak preview when we saw 24 days with at least 1 inch of rain. The average will be, we'll see a 30 to 40% increase by later this century, depending on the scenario. Sea level rise. The chart you see here on the top shows projections for sea level rise by 2100. Based on different emission scenarios, on the low end, we'll see about another foot of sea level rise. On the high end, we'd see 5 to 6 feet of sea level rise, which is a lot, and would be a lot to adapt to, not just here in the DC area and along the Chesapeake Bay and the Potomac, but for all coastal communities all around the world. It'd be expensive and very disruptive if these high-end sea level rise scenarios play out, and they're dependent on how quickly the ice sheets in Greenland and Antarctica melt. And there's a lot of uncertainty about how fast they're going to respond to the amount of warming that's occurring. Some models think the melting will be slower, some think it will be faster, and that's why you have such a big range as to how much sea level rise we'll see. 1 foot's manageable. We've dealt with that over the last 100 years. We've seen a foot. If we see 4 or 5, 6 feet, that's a lot more to deal with. Reports from NOAA, we talked about high tide flooding increasing rather remarkably already just due to that 1 foot increase in sea level rise. A report from NOAA put out a couple of years ago found that by 2100, high tide flooding will become or exceed on average every other day flooding under an intermediate low scenario. So basically, now we're seeing 6 to 10 days per year where we have high tide flooding. By 2100, half of the year, and that's under an intermediate low emission scenario. So that's kind of assuming we slow our emissions down some. If we don't slow emissions down some, if it's business as usual, high tide flooding is every day in places like Annapolis, Georgetown, and Old Town. This is just a visualization of what different amounts of sea level rise would look like on the downtown mall, assuming no adaptation to hold back the water. And you can see that's what today is. There's 5 feet. And 5 feet is plausible if the more aggressive sea level rise connection scenarios are right. Now, we wouldn't see 12 feet this century. That I haven't seen any models which show that. But when we could see 12 feet is when a hurricane comes up the Chesapeake Bay. In fact, during Isabel in 2003, we had a 9-foot storm surge move up the Potomac. And so the hurricane, you could see that type of flooding in the absence of any adaptation to hold back the water. One other thing I should mention, I'm about done. Showed you a lot of slides, but thanks for bearing with me. Stronger hurricanes. I mentioned the fact that, if you have a hurricane, which hits the North Carolina Outer Banks and then it moves north right up the Chesapeake Bay and tidal Potomac, that can push a big storm surge and result in a lot of coastal flooding. Well, hurricanes are projected to get stronger, and we're already seeing that. And with stronger hurricanes, that means heavier rainfall affecting larger areas. Stronger winds, on average, projections suggest about a half category increase in hurricane intensity in terms of wind speed by the end of the century. More rapid intensification events where hurricanes start off are like a category 1 day, and 24 hours later they leap up to 3, 4, or 5. We've seen an increase in those rapid intensification events in recent years. Hurricanes are relatively infrequent here in the DC area. We tend to get the remnants, but for places like Florida, the North Carolina Outer Banks, the Gulf Coast, that likelihood of more rapid intensification events could have serious consequences. And then there's the higher storm surge due to higher seas, hurricanes pushing a lot of ocean water inland. And if the sea level is already higher due to climate change, that just increases the amount of inundation. Climate models generally don't expect a change in frequency. They just expect the storms that form to become more intense, all other things being equal. So some conclusions. Carbon dioxide and other heat-trapping gases are accumulating in the atmosphere. We saw that 50% increase in CO2 since the 1700s. Planet's warming, almost certain to warm more. We're seeing that here at the local scale here in DC. We're seeing more hot days, heavier rain, and higher seas. That's going to continue. We need to adapt to and plan for these changes. The work that John talked about in the beginning is really critical. And if we want to reduce, and the best way to reduce the risk of the worst and most unwelcome changes is to slow this down. And that's by reducing emissions of greenhouse gases. We've got to adapt, but we also want to hold the amount of warming and the amount of change we see in check by reducing emissions. And more solar, more wind, more electric cars, all those types of technological things. We need to implement those as fast as we can. So I will stop there to leave some time for Q&A, and I will stop sharing my screen if I can figure out how to do it. Thanks so much.
Thank you, Jason, for a very detailed but nuanced presentation on how climate is changing in our neck of the woods. And it is very nuanced. The whole issue of climate change, I want to ask you, Jason, when I was a freshman at Montana State University in 1994, that's 27 years ago, I learned in Climatology 101 that climate change, global warming is occurring because of increased concentrations of CO2. And man was probably, we didn't quite know in 94 it was man, but by 96, 7, pretty much 30 years on of failure of the science community to communicate effectively, also with some very strong opposing forces and disinformation out there. Seems like today, last couple of years, with the wildfires and the freak blizzards, which are linked to climate change, the jet stream's all out of whack, right? Sinusoidal. Do you think we're at a tipping point now at 420 ppm? And
yeah, I mean, I think so. I mean, I think the weight of the evidence is pretty overwhelming now. And I just think that, you know, with all of the extreme weather we're seeing so often and in so many places, it's becoming harder and harder for people to reject this notion that, you know, man-made climate change is impacting our communities. I mean, I think, you know, when we look at what's happening in the West and you see places like, you know, Seattle and Portland blowing through all-time records by, you know, 5-10 degrees.
yeah, it's crazy.
Yeah, and when you see the, you know, the frequency of these, you know, just extreme flooding events like we saw in Germany and Belgium, and then we saw in China, and it's kind of like playing whack-a-mole. I mean, they're just like these unprecedented weather extremes are just happening all the time, and more so than we've ever seen. And so I think the evidence is becoming pretty undeniable now. And I think it's just a matter of, you know, like, I think the debate isn't whether it's happening, it's, you know, what are the best ways to slow it down, and what are the most effective strategies? What's the role of governments?
Yeah, let me ask you one follow-up, and then I'm going to open it to the floor, everybody.
Sure.
But I saw a fascinating interview with Governor Schwarzenegger, who, you know, in California, they led the charge with AB 32. And he said the way they framed the issue in California is that he called carbon dioxide pollution. It is pollution. And when people heard the word pollution, they thought of things that, you know, you choke on or kill you.
Right.
What would you recommend, or what would be your ideas on how, you know, 30 years on, we can reframe this issue?
Yeah, I mean, I think, you know, if you had asked me, you know, a couple decades ago, I would have maybe been reluctant to consider it pollution. But I think now I've kind of I've changed my viewpoint's changed on that. You know, first of all, the EPA recognized carbon dioxide and greenhouse gases as pollution under the Clean Air Act, so that happened. Now, it depends on how you define pollution. So if you define pollution narrowly, it's just something which, you know, is harmful to you when you breathe. Carbon dioxide isn't harmful in that way, like, you know, ozone is, or particulate matter. But on the other hand, when you look at the effects that carbon dioxide has on the environment and how it's endangering human health and welfare by increasing the intensity of our weather extremes, it is pollution. And I think if you use that broader definition, by not just thinking about, okay, is it something we breathe, but is it something that impacts our human health and welfare through changes in weather and the environment, then I think it most definitely is pollution. So I accept that broader definition, and I think it is effective because it reaches people. Because if you just talk about CO2 and don't talk about it, how it has harmful impacts, and you don't sort of give it you don't frame it negatively, people might not understand it otherwise. So I'm with Schwarzenegger on that.
Okay, great. All right, so looking at submitted questions, anonymous attendee. My friend in Ashburn has noticed that rainstorms dry up before reaching her area. She gets no rain, even though the rest of the area does. Are there extensive, severe storms out there effective? So the snow hole, Jason, Is the snow hole, is it getting worse because of climate change? Is it getting bigger?
Yeah, so I mean, I think like if you know, if you live close to downtown DC, um, you have several things working against you when it's when you have snow events. Number one, it's warmer downtown, and if you live sort of within the Beltway, it's warmer. You have lower elevation, and all of those factors means that it's going to be harder for the snow to stick and to accumulate. So sometimes we'll have snow events where you know, Reagan National, downtown DC, you have bare ground, but you just go a few miles to the north and west into the colder suburbs, and the snow's accumulating. So, and we're seeing more of these marginal events where it's just barely cold enough to snow. So,
Yeah.
if you're a couple degrees warmer, you're at a lower elevation, and you're in a place which is being impacted by urban heating. Yeah, you're going to get less snow. So the snow hole is real from that respect, and that places like, you know, near downtown Washington are just going to get less, especially when it's not super cold out. If it's around 32, 33, you're going to get more snow in Fairfax and Burke and Gaithersburg and places like that, Ashburn, than you will in South Arlington, Alexandria, and DC.
Great. So let's see, Barbara Moreau. I hope I said that right. This is an interesting question, and I've been racking my brain over it, Jason, since you submitted. But and you talked about humidity and the increase in humidity with climate change because of evaporation and the atmosphere's ability to hold more moisture. How does the urban heat island effect impact humidity?
I don't think it impacts it a lot. I mean, the one thing because the atmospheric moisture is pretty well mixed and distributed. So, but there's actually some research, and there's some actually compelling evidence that the heat island can enhance thunderstorms when a thunderstorm moves over downtown, because it's hotter over the city and there's more heat and instability, and so that can make the downpours heavier downwind. So if a storm moves from the west over DC, it kind of draws in some of that heat and instability. The storms can be stronger for places like Prince George's County, Southern Maryland, as they continue to the east. So in that sense, heat island can affect storms. In terms of humidity, I don't think there's a big effect there.
You think at the surface, like at the sidewalk level, it's so hot that it dries the air out?
Yeah, I mean, probably. I just like the amount of water vapor. Water vapor is pretty well.
So mixed,
it gets pretty well mixed, and so I guess if the air was a little stagnant, I mean, if it's hotter, it's going to be, all other things being equal, it's going to feel more. Your heat indexes are going to be higher with the same amount of moisture. So.
All right, thanks. Let's see. How will sea level rise impact communities along the Potomac River like Old Town, Alexandria, but also on local tributaries like Potomac Creek and Stafford, where an NVCT easement protects one of the largest blue heronries in the Chesapeake Bay watershed?
Yeah, I mean, you know,
I want to just say one thing before you go. I think this is like the elephant in the room, Jason, with climate change. Most people have no idea that the Potomac River has a tide.
Yeah, for sure.
I teach my students, they don't know it's connected to the ocean.
That's exactly right, because the water comes right up into the Chesapeake Bay into the tidal Potomac, and so basically as far north as Georgetown, right, or a little bit farther north, you're getting tidal water, and so sea level can affect all of those areas. I think, yeah, I mean, you know, we've had a foot of sea level rise in the last 100 years. I think we'll have at least a foot in the next 100 years, probably more, especially if the ice melting of the ice sheets accelerates and the oceans expand further as the climate continues to warm. So I think 1 to 2 feet conservatively is what we're looking at. And if there's sort of an abrupt increase, it could be more. So yeah, I mean, it's going to be, it's going, as a couple of my slides show, it means that you're going to see a lot more high tide flooding in places like Old Town, Georgetown,
and storm surge.
Well, yeah, and the big concern is going to be storm surge, because if you get a tropical storm or hurricane moving in, um, those by themselves will push the water up by several feet, and then you're adding the impact of sea level rise on top of that, so you're getting another foot or two. So yeah, there's just more, just means more inundation, more flooding, more cleanup, and more cost, because we're going to have to hold back the sea.
Here's a great question, because I think oftentimes people get confused between weather and climate, and was one event linked to climate change or was it not? And
Yep.
Gary asks, can you talk about the storm on Monday? That one that blew up over Pittsworth and dropped off like 100 trees. And can you talk about the strong storm Monday night and whether that was related to climate change?
Yeah, I mean, that's probably the toughest, because I mean, climate change, so climate change is always in the background now, right? I mean, we're warmer now than we would have been 100 years ago. So because it's warmer, for any precipitation event, that just means that there's a little bit more water in the atmosphere available to these storms, which can make them heavier. So I saw some exceptional rain rates on Monday. I saw 2 inches of rain in 20 minutes, which is a lot. I mean, that causes flash flooding in Petworth. And so basically for every degree it warms, I think you get 7 to 8% more water in the atmosphere. So so basically, you know, we've warmed a degree. So pretty much all of our precipitation events are, you know, at least 7 to 8% heavier than they used to be. That makes sense.
Yeah. I'm just scanning through the questions. We got a couple minutes left. Alan Rosum, did you have a question?
I mean, I think there's a couple here that maybe John or more you and me to answer as opposed to Jason, but I think there's a couple of questions about, permeable surface and how do you deal with the fact that, costs are so prohibitive to do the right thing. What's the market force that drives that down so that people are actually, not creating as much impervious surface, and is it just cost based, or is it market forces? And maybe something about that. But for those that have answered that question, if we need to go get more detail on it from other sources, we can do that and post.
Well, I can tell you how the city of Falls Church has dealt with impervious surfaces. They've taxed it. They're disincentivizing parking lots, and they included churches. It's not a tax. They called it a fee because we have a lot of churches in Falls Church, and the churches would have been exempted if it was tax. But to disincentivize driveways, roofs in Falls Church City, we pay a stormwater tax. So people are putting in permeable driveways. You get credits if you put in rain gardens. So churches have been putting rain gardens on the perimeter of their parking lots to capture that rain so it doesn't go into the stormwater system. And if anybody in the chat has any examples from their local jurisdictions or their background.
That's great. I think there's another one here for Jason that might be good. Seeing more stories about various countries actually planning to seed clouds to prompt rain in drought affected areas. Like, is that an actual successful strategy, and does it have unpredictable impacts?
Yeah, I mean, I think it's controversial. There have been studies which have shown demonstrated some limited success for that, but sometimes it's unclear, how effective those strategies actually are. And I think among the technology is solid, it's sound, that and it can work. I think the question is, like, how effective is it, and are some of the results that some of the countries are claiming actually real? And there is a concern about unintended consequences of it. If you see clouds in one area, does it mean that other areas get less rain because you see clouds? And so there's some thorny issues to work through. Honestly, it's not an issue we've written about recently, but so I think it's one we should pick up because we're seeing reports of this coming from like China and from the Middle East. And some extraordinary claims are sometimes made, but the evidence of how effective these are still to be determined, I think. So it's sort of it's a work in progress. That's kind of how I'd describe it.
In a Jason, in a unpublished Capital Weather Gang article I was researching, I was going to write one on cloud seeding, and I reached out to Vail because I have a contact, and I talked to they seed clouds. Vail Resorts does, and several other ski resorts in Colorado do, and they send silver iodide from canisters at ground level. They don't fly planes.
Yep.
And they claim they can increase their snowfall by 10 to 15%, which they average about 300. So that would be another 3 feet of snow. You know, they claim it's effective.
Yeah, exactly. So, like,
the snow may be different than rain.
Sometimes you see reports out of China, like with really sort of extraordinary claims about how successful and effective it is. And I think there's some skepticism from the scientific community about that. But I don't think there's anyone that doubts that it doesn't have some effect and it's not helpful. I think it's like, it's a degree in the magnitude of it, I think.
When I worked at NCAR, we had a guy who was using those flares that go on the wings that seed the clouds at Marshall Field Laboratory, and almost caught the prairie on fire.
Oh, gosh.
With those things. We had to put it out. We had to put the fire out with de-icing fluid we were doing experiments on.
Crazy.
Well, we don't want to be doing that. I really appreciate Jason and John being with us. I think the experience and the expertise, on that panel between the two of them is really significant. And there's some other questions in this chat that we'll try to get answered offline. NVCT is really working, I think, at the nexus of a lot of this, because we know that, permanent land protection lessens climate change impacts, whether that's expanding wildlife habitat for resiliency, combating urban heat island effect, creating natural and efficient stormwater runoff, and then buffering for coastal and low-lying areas from severe storms and flooding. We know that we need to be stepping up and doing even more to protect land and water resources with everything that Jason and John have laid out here. And that's an imperative for us that we hope you as our members, followers, supporters will continue to engage with us on and ensure that we're doing that work, and hopefully doing it in a scientific way where the places that we're protecting really are the most important that will have a climate impact. And that's something we're working on as well, with better mapping and better GIS technology than ever before. So there's so much more we could get into with this presentation. I want to thank Jason Samenow and John Hopewell for leading us through this. We will post this recording on our website, and we'll get it around so that others can take advantage of it, and appreciate their time and appreciate the interest of those listening. We hope to bring you more sessions like this, and continue to both educate and learn more about the opportunities that we've got to protect our region and certainly understand the impacts of weather and climate. So thank you all for being with us today, and we hope you stay cool out there. Have a good afternoon.
Thank you, everybody.